I want to show you something very interesting. I have here two tones that differ by a frequency of 3 Hz. Have a listen to the first one. And now the second. Now, if you're perceptive enough, you might have been able to make out the slightly lower pitch of the second tone. But something truly odd happens when you play them both together. We get some sort of rhythmic change in loudness. But why does this happen? Let's think about what sound is. A pure tone is a sinusoidal oscillation of air particles at a given frequency. Although we have a limited hearing range, this frequency can in fact be anything. Now, the loudness of a sound is related to the amplitude of oscillation. It's proportional to the amplitude squared. It's important to keep in mind that the loudness does not depend on the displacement at a given time, but the amplitude or the maximum displacement of the wave. So, what happens if we have two tones playing simultaneously? Well, the principle of superposition of waves tells us that we simply add the displacement contributions from each wave at each point in time. I also want to show you a different way of representing the sound wave. Consider a complex number that rotates in a circle with time at the frequency of the oscillation of the air particles. The imaginary part of this complex number encodes the particle's displacement with time. The number's distance from zero, or the radius of the circle, is the amplitude of oscillations. You might recognize the expression for such a number. It's the radius a multiplied by e to the I times 2 pi times the frequency times time. Again, the amplitude of the tone is the distance of this number from the origin, which is denoted by the modulus of this complex number we just called psi. And in case of a pure tone, it's this radius a. Now let's see what happens when we add two tones. We'll have a tone with a frequency of 1 and another with a frequency of 2, both having an amplitude of 1. We can add the complex numbers, real plus real and imaginary plus imaginary, and plot the modulus of this new sum psi with time. They begin both pointing in the same direction, giving a modulus of 2. After a quarter of a second, one has rotated a fourth of the way around the circle, while the other has rotated half the way around. Now they don't both point in the same direction, so the modulus is less than 2. After half a second has passed, one number has rotated half the way around the circle, while the other has made a full rotation, meaning they are pointing in exactly opposite directions. The modulus of the sum is now 0. If we continue plotting this, we see that the modulus of the sum, which we liken to the amplitude of oscillations, varies with time, being maximized at integer values of t, and being 0 at half more than integer values of t. Let's see if we can mathematically find this relation between amplitude and time. The math is slightly convoluted, but it simplifies well in the end. The modulus of psi is equal to the square root of its real part squared plus its imaginary part squared. You can use Euler's formula to get those as follows. Then we can expand the binomials. We notice here two Euler identity pairs, each simplifying to 1. Then we can factor out a square root of 2. And we can use the identity for the cosine of a difference in angles to condense this mess a little. Simplifying a bit more. And finally noting that the cosine of a negative value is the same as the cosine of that value, we get this final expression for the amplitude of the sum of these two tones with time. It's the square root of 2 times the square root of 1 plus cosine 2 pi t. Let's consider a more general case. We have the sum psi of two tones with amplitudes A and B, and frequencies f1 and f2 respectively. What happens to the amplitude of the sum then? Again, using the same methods as before, we take the modulus of psi. This time, we have the individual amplitudes in our expression. We expand here again and combine the like terms, and we use our nice cosine identity here as well. In the end, we end up with this expression here. The amplitude of psi is equal to the square root of a squared plus b squared plus 2ab times the cosine of 2 pi times f1 minus f2 times d. Since cosine ranges from -1 to 1, we can note that the minimum value for the amplitude would be the square root of a squared plus b squared minus 2ab, and the maximum value would be the square root of a squared plus b squared plus 2ab. We can rewrite these bounds using the sums and differences of the squares of binomials. In the end, the bounds simplify to the absolute value of a minus b at a minimum and a plus b at a maximum. So that means you can only get the sum of two tones to dip periodically to 0 if they're of the same amplitude. Interesting, no? Also from this equation, we notice that the frequency of this changing amplitude is equal to the absolute value of f1 minus f2. Again here, the absolute value is because cosine is even. It doesn't care if the difference is negative. This also means that if the two frequencies are equal, then the amplitude is constant and does not change with time. So, coming back to our beats, I think you can guess what's happening. Adding the two tones with their slightly different frequencies leads to them cancelling out with each other at times and adding up at others. Although this happens at a higher frequency than we've seen earlier. This frequency is, as we derived, going to be 440 minus 437, or 3, which sounds about right. Let's get an overview of what we did. Firstly, we notice beating when playing two tones with similar frequencies. Next, we understood tones as sinusoidal waves that add when superimposing. Then, we represented a tone as a complex number, rotating with time, with its modulus being equal to its amplitude. After that, we added the complex numbers representing two tones, and noticed how sometimes they point in the same direction, adding up, and other times they point in opposite directions and cancel out. Finally, by finding the modulus of the sum, we found a way to determine its amplitude over time, and found parameters such as the minimum and maximum amplitudes, and the amplitude's oscillation frequencies. Now, before ending this video, I want to leave you with two challenges. Number 1, try to discover what happens when one of the waves is shifted by a phase shift of phi. And number 2, see if you can find an expression for the amplitude when there are more than two tones involved. Good luck!